we're looking at graphing relationships, and we're looking at some examples and how to interpret those examples and how to interpret those relationships and write them in graphs. So I'd like to start out with a few examples, and we're going to label these 1 through 5. We'll start out with example 5 first and work our way through. So the first example, example 1, again, you'll find that in your classwork as examples for today, is this. It's a little graph, and it says it's the distance a delivery van is from the warehouse varies throughout the day. The graph shows the distance from the warehouse for a day from 8 a.m. to 5 p.m. So I took my graph and I just kind of wrote on a little bit. My x-axis represents the time. In other words, my horizontal axis is showing the time. The time starts at 8 a.m. and ends up in 5 p.m. You know, we might not always write it that way. We might put it in terms of minutes, but that's what I did. I just wrote 8 a.m. to 5. And then notice we have the vertical axis, or the y-axis, is in terms of distance. Now we're talking about the distance it is from the warehouse. All right? So for example 1, we're going to answer just a few questions. First question we're going to answer is this one. Segment 1 shows that a delivery van moved away from the warehouse. The question is, what does segment 2 show? So write that down. Question number A is that. And so we're looking at the graph itself. What's going on here? Well, it leaves the warehouse, and in whatever period of time it takes to get from here to the start of segment 2, it's moving. Now, is it moving away from the warehouse, towards the warehouse? Well, if it starts at the warehouse and the distance gets farther, it has to be moving what? Away from the warehouse. All right, so we see that it moves away from the warehouse, and this line is fairly steep. And then on the second segment, it's not quite as steep. So in that period of time, it hasn't quite gone as far. Well, here's one thing I want you to write down. This is something for you to remember. First of all, in middle school, you were taught a little bit about slope. But slope is really just a rate of change. Everything in some shape, form, or fashion is a rate of change. I mean, you understand that, because if I told you right now that I drove to school at 95 miles an hour this morning, what would you think?
How were you not arrested?
How was I not arrested? You should think that. I didn't say I drove 95 miles an hour, but if I told you that. You know, we understand rate of change kind of like this graph, because if I drove at that speed for an hour, how far have I driven? Who knows? Yeah, I'll ask that question again. If I drive at 95 miles per hour and I drive for an hour, how far have I driven?
95 miles.
Yeah, absolutely. 95 miles. Perfect, Octavian. Exactly. And so that's pretty fast, right? And I would have gone 95 miles an hour. That's much further than if I was driving at 35 miles an hour, isn't it? Because if I was driving 35 miles an hour, after an hour's period of time, I will have traveled 35 miles. Here's what I want you to get. The slope is the rate of change, and we've looked at slope before in middle school, but the steeper the slope, the higher the rate of change is. Okay, so in this second segment, segment 2, I'm still moving away from the warehouse, but I'm doing so slower than segment 1. Okay, so I think that kind of makes sense. So the steeper the line, the faster I'm traveling. Does that make sense? So then what happens right here with segment 3? It's flat, isn't it? What's going on there?
It's static.
Static, or I have stopped, right? So that zero slope means I'm not moving at all. We'll come back to that in just a minute. All right, so what about this? Second question I want to ask you. This is the B question. Based on the time frame, what change in the distance from the warehouse is represented by segment 6? So looking at this graph, what's going on right here in segment 6? Tell me. Am I moving? Has my direction changed? Because remember, this vertical axis, we're talking about distance. Okay? So if we're talking about distance, then what's going on is the distance has decreased. So in segment 1, I was moving away from the warehouse. Segment 2, I was moving away from the warehouse. Segment 3, I'm still. Segment 4, I'm moving away from the warehouse quite a bit quicker, probably the fastest so far there in segment 4. And then segment 5, I'm stopped again, but what's going on in segment 6? How am I moving? Not necessarily slower. How am I moving in segment 6? Am I still moving towards the warehouse, or is my distance getting smaller? Do what? It's getting smaller. So if it's getting smaller, then I'm what? I'm coming back to the warehouse, right? So for B, segment 6, I begin returning to the warehouse. In other words, I start my return trip. So I've sort of already alluded to this next question, but you can answer just the same. The question is this: which line segments show intervals where the distance did not change? So which line segments show intervals where the distance did not change? Can you tell me? I'll wait on an answer for somebody at home. Somebody unmute and answer that question. Which line segments did show intervals that the distance did not change? Jaylen, I'll ask you. Which line segments here on this graph? Okay, we're looking at the graph. Let me show it to you just a little better, maybe. That might help. Where is it on that graph that the distance doesn't change?
5.
Yeah, 5 is one of them. There's a couple more. Do you see any more there?
7.
Yes, and?
8. No.
Not 8.
3.
3. Yeah, you got it. So the intervals that the distance doesn't change, those are 3, 5, and segment 7. So segments 3, 5, and 7. The distance doesn't change. How did you know that? What is it about it that tells us the distance doesn't change? Yeah, exactly right, Octavian. It's flat. So this has no slope. we're getting nowhere with, well, not no slope. It has a zero slope. Excuse me, that was an incorrect statement, mathematically speaking. It has zero slope, meaning I'm traveling 0 miles per hour. And so an hour I go 0. Same thing is true with this. It's level, it's flat. So the distance isn't changing in segments 3, 5, and 7. And the last question that I might ask, and you got to be a little bit creative here. This is where we get to have fun. Okay? What's the possible explanation for those segments that do not change? How can we explain that? Why is he driving and suddenly the distance doesn't change? What's going on? Is he moving or is he? So what's an explanation? Is he moving? Yes or no? No. So we call that he stopped, right? So he stopped, and we could even say maybe he's having lunch. Or he wants to stretch his legs and walk. Or maybe he's stuck in traffic. We don't know, but for whatever reason, he's not moving. So just some ideas of why he might not be moving. So really, graphing these relationships, it's really not that difficult, is it? Let's look at another example. This one's a little different from that one. Zoom in a little bit so you can see it a little better. I like to fill up the screen if possible. So we like to draw graphs of real life situations. So in this example, it says this is actually example number 2. 3 hoses fill 3 different barrels of water, or water barrels. A green hose fills a water barrel at a constant rate, and a black hose fills is slowly opened when filling the barrel. In other words, we just barely turn the water on and we keep turning it on. Okay. And then a blue hose is completely open at the beginning. They open at full force and then it's slowly closed. So the 3 graphs of those 3 situations are shown here. So which graph represents the amount of water that is turned on at a constant rate? A, B, or C? Do what? That's my answer. Let me say it again. You got the green hose that's filling the barrel at a constant rate. The black hose that's filling the barrel, it's turned on slowly at first and then keep on turning. Or blue hose that's full force. Luke, what do you think? B, yeah. That's the constant rate. What makes the constant rate? Well, the line is straight. And we're comparing time to the amount of gallons coming out of that hose. And we know that before we turn it on, that the time is 0 and there's no water coming out of it, and we turn it on, but that's a constant rate. So a straight line shows us that, okay? So if that's the constant rate, what about A? A is what? Is it slowly turning the water on, or is it turning it on at full force and then turning it back?
It's the latter.
Okay, so with A, I've turned it on slowly or full force? Yeah, definitely. So because there's not a lot of water coming out, and I keep turning it on, and so that means C represents, hey, I just cranked that thing full blast. You ever done that with a hose? Just turn it on full force, But then we've eased back off of it and started turning it down. So here's what I want you to write down for example 2. Okay, so graph A represents the black hose. And it's slowly open. So you might need to jot that down right quick. So that's the slowly opened one there. Graph B represents the green hose. And it's a constant rate. And graph C represents the blue hose. And it is completely on at first. Then slowly closed. One more question. Write this down, please. Could a graph for the amount of water slant downward from left to right? Is that possible?
Yeah.
Okay.
Now, in this given scenario,
Can you explain that scenario for me?
so the graph could slant downward if the water level was decreasing.
Exactly.
But by definition, the water level cannot increase
Mm-hmm.
when you are adding more water.
Exactly.
It cannot decrease.
But if the water's decreasing, we could actually be draining that barrel, right? Decreasing, ing. So if the water level decreases, it would slant down, and we could be actually draining the barrel. Couldn't we? So the amount of water could slant downward from left to right. If the water level is decreasing, we could actually be draining that barrel. So we could have a graph like that. I kind of like this next example. I don't know why I like it so much, but I just think it's kind of a cool example. So you and a friend are playing catch, and you throw 3 different baseballs to your friend. You throw the first one, it's in an arc, and your friend catches it. You throw the second one in an arc, but this time it gets stuck in the tree, and you throw the third ball directly at your friend, but it lands in front of your friends and rolls the rest of the way on the ground. All right, so 3 different situations. Let's talk about what that might look like if we graph it. So we throw a ball, a baseball of some sort or another, and when we do, the first time we throw it, it has this just perfect arc. Okay? And then the second time we throw it, it gets stuck in a tree. Third time we throw it, it just lands on the ground. Now, I'm going to show you 3 different graphs, and my question is this. And this is example 3. All right. So the question is this. which graph shows where it gets stuck in the tree? A, B, or C? Somebody at home answer that question, please. Which of those three graphs, A, B, or C, is the graph of when the ball gets stuck in the tree? Yes, Dominique put in the chat. And it is C. Well, here's what happens. First of all, it starts off above zero because the guy's throwing it, right? And so he's, 4 foot tall, something like that. So he throws it and it goes up in the air. Remember, my y-axis here is the height, and my x-axis is my time. As it's going in the air, it flows along pretty good. And then suddenly it gets stuck in the tree and it stays the same. So it's stuck in the tree in graph C. Well, what's going on then in graph A? What do you think? Which situation is that? What happened there?
You threw it and then it rolled on the ground.
Yeah, exactly. You threw it and it rolled on the ground. Perfect. You can even see it hits the ground and the line here goes on out a little bit. Well, what about graph B? Well, that's my perfect arc. It even looks like what it says. Throw it to your friend, it makes this perfect arc. That's pretty simple. Well, graphs are designed, what we're looking at in this lesson today is to represent real world situations that are, lots of those graphs, everything we've seen, these graphs have been, drawn without any interruptions. In other words, we called that yesterday when we defined it, and you may not remember that, we called it continuous graphs. So a continuous graph is made up of a line or connected lines and curves. But other types of graphs are not continuous. They're actually made up of distinct and unconnected points. So these graphs, well, they look a little different. They're made up of dots. They're called discrete graphs. Let me show you an example of that. Okay. So this is a graph. Let me read to you and explain to you what this is a graph of. This is a student taking a test. This could actually be you today taking your quiz. And there are 10 problems on this test. And for each problem the student answers correctly, the student receives 10 points. Okay, so if they get none of them correct, my x-axis now is not time, but rather the number correct, I get 0 points, right? But if I get 1 correct, I get 10 points, 2 correct, 20 points, 3 correct, 30 points, 4 correct, 40 points, 50 points, 60, 70, 80, 90. If I get all 10 correct, I get 100 points. That kind of sounds familiar. And so this graph is a discrete graph because it's made up of unconnected points. Now, I don't know about you, I always have to do something to remember things, okay? So here's what the way I kind of remember it. A discrete, write this down, please. Graph is disconnected points. If I use the word disconnected points, it's helpful for me because discrete begins with the letter D and disconnected begins with the letter D. All right, so a discrete graph is disconnected points. And then a continuous graph is made up of connected points. And for that, I think about the C for continuous, C connected. So if that helps you remember the difference, then by all means, use it. So this graph of these test problems, this is definitely a discrete graph. But it also adds one other thing, and the question actually here says to tell me if is it continuous or discrete. So for example 4, I'm going to state first that it is a discrete graph. And then it asked me to do one other thing. It asked me to state the domain and the range. Now, the domain, yesterday, by definition, is the first coordinate of the ordered pair. Now, for graphs, typical graphs, we'll label the horizontal axis, the x-axis, that's the first coordinate, and the second coordinate we'll label as the y-axis or the vertical axis. So looking at this graph, then, my x-axis is the numbers of problems correct. And so if I'm going to state the domain, these are individual points here. And the only thing that I care about in the domain is the first of the coordinates. In other words, what are the x values? I don't care about the y values in the domain. That's the range. So in domain, I just want to know what are those first values. Well, first value could be 0. It could be 1. It could be 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of problems I have. Okay? So that's the domain. The range, then, is my second coordinate of my ordered pair, or in this case, the y values. Again, I don't care about the x in the range. I'm just looking at the y values. Now, this first point has a y value of 0, just like the x value, but my y value for the second point, that's point 110 because it's 10 points for each problem. So my y value there is 10. My y value here is 20. And so on, 30, 40, 50, 60, all the way up to 100. So that's my range. It's a discrete graph that has specific points for the domain and the range. Well, let's tie all this up with one last problem. The first thing we got to determine here is the question I'm asking you, or the graph, what's it going to look like? Will it look like a discrete graph? Will it look like a continuous graph? And then we want to state the domain and the range, and that may change depending on the kind of graph. And actually, my instructions will be to you just to sketch a graph. Okay, so we can do that. And it's going to look like this. So let me show you the problem itself. Now, a bathtub is being filled with water. And after 10 minutes, there are 75 quarts of water in the tub. Okay. Then someone accidentally pulls the drain plug while the water is still running. The tub begins to empty. And then the tub loses 15 quarts in 5 minutes. And then someone puts the plug back in, and the tub fills for 6 more minutes, and it makes another, or rather gains another 45 quarts of water. Well, after a 15-minute bath, the person gets out, pulls the drain plug, and it takes 11 minutes for the tub to drain. Seems like a long time for that tub to drain. But anyway. So we want to graph that, okay? And they've basically given you a graph to start out with. I'm going to sketch my own graph. And I'm going to use the same measurements or markings, same tick marks that they use for my graph. Okay, and I know it's an X and Y. And out the X portion, they start at 0, and then they mark this off every 5.
Attention seniors, can our students Branton, Matthew Kinsler, and Cooper Campbell come to the upstairs freshman academy? Thank you.
Okay, so this represents the time in minutes. And my x-axis typically does. It doesn't have to always, but we might not be talking about time. And my y value is going to represent the water in quarts. Okay, so, and this is my 5th example. And the graph I had there was broken down by 15, so it's 15, 30, 45, 60, 75, 90, 105, 120. And I'll just mark every other one. So those are just evenly spaced tick marks there. And I'll refer back to the problem that I read to you a minute ago. So a bathtub is being filled with water after 10 minutes or 75 quarts. So I know that when I first start out, that I have no water and I have no time. In 10 minutes, it will fill up to 75. So I know this is 60 plus 15, 75 is this first tick mark right here. All right, so it goes from 0 to 75, just like that. And it's a continuous fill, it says. And then it says that after those 10 minutes, someone accidentally pulls the plug and starts to drain. So for the next 5 minutes, it loses 15 quarts. So it's going to come down 15. So it comes back down to 60 in the next 5 minutes. So we go 10, so 5 minutes more would be 15 minutes down to 60 right there. And then someone plugs the drain, and for the next 6 minutes, so up to 21, which I'll approximate to be right about here, up to 21 minutes, it gains another 45 quarts. So 60 plus 45 is 105. I've got 90 here. 105 should be this tick mark here. So we're going 21 to 105, be right about there. Remember, I'm just sketching a graph, so my graph may not be absolutely perfect. And then for the next 15 minutes, they're taking a bath. And so while they're taking a bath, what does my water level do? Does it get better or worse? Does it get more or less? What happens? If I'm taking a bath, the water what? It doesn't drain, does it?
No,
No.
it stays in the thing.
Yeah. Yeah, it's going to stay the same unless it's a bunch of, little children and they're splashing all the water out or something like that, right? Yeah, so we're assuming this is an adult person. It's not going to do that. So for the next 15 minutes, so that's 21 to 36, which is approximately here, the water level does not change at all. In other words, it's just flat, just like the distance was earlier. Nothing's changing. We have no rate of change there to right there. All right, and then it takes 11 minutes for that tub to drain. So that's 36 plus 11. So that's going to be 46. Need one more tick mark here and probably about there. And at 46, it's drained. And the whole thing drains over that next 11 minutes. So there's no water left in the tub. So the first question I would ask you is this. This graph, is it continuous or discrete? Yeah.
Alexa,
Do you have
play graph.
a question?
Alexa.
Hang on just a second. Okay, so that graph is a discrete graph. Is it a discrete graph? No, it's a continuous graph. Just checking to see if you're paying attention. Yeah, distracted. So it's a continuous graph. So the domain, we're going to have to write an interval notation. All right, so if we're writing the domain in interval notation, it starts at 0 and goes to 46, correct? So I'd write it that way. The range, well, we started with no water, okay? And its 2 starts at 0. I'm using brackets because it's equal to 0. And it gets a maximum of, we said, 105 gallons. One of the things that might be helpful to do is to actually, state the points here. This point, first point is 10. This coordinate is 1075. The second coordinate is 15. It came down to 60. The next coordinate is 21. It's 105, and it stays that way for 15 minutes till it gets up to 36. And it's still 105, and then when it drains, back down here to 0 and 46. So the range, the most water, the highest, the most amount on the y-axis, the highest it got was 105. And so we just want to know what it spans in regards to the y-axis. For range and domain, we want to know what it spans in regards to the x-axis. And so we have a continuous graph that has a domain from 0 to 46 and a range from 0 to 105. And so with that, that's pretty much how we graph relationships. Any questions? All right, so pretty much that's pretty straightforward. So the next thing we'll do is give you a chance to work the assignments that's in the classworks and give you a few minutes to work on those and ask questions. And in that classwork assignment, you will be graphing relationships and using graphs to interpret relationships.